This is part 2 of the ellipse section. We're going to be dealing with applications of ellipses. Number one I talked about, the last one was when you had like the Oval Office, whispering galleries. They're all sounded. Focus is back out on the other side of here. Now, one thing you remember, you should have picked up from the reading, is that one of the basic definitions of an ellipse is that for some point here, the distance between P and, let's call this focus 1 and focus 2, plus distance from P in focus 2 is a constant, and it happens to be 2A. This is one little formula you're going to need to know. But the sum of all these distances in an ellipse is the same. Now, the other application I want to talk about, and it's one you're going to see a lot of in this one, is actually orbits in the solar system. Now, if you look at the Earth's orbit, the orbit around the Sun, when people talk about the Sun is at the center, but it's actually not. The Sun is at a focus, and the Earth orbits in an ellipse. It's got an elliptical orbit. The distance here, the shortest distance between the Sun and the Earth, is called perihelion. Helium for the Sun. If you're dealing with the Moon, it's called perihelion. And the farthest distance that the Earth gets is called the aphelion, or the apolluna, or if you're dealing with orbiting around the Sun. Okay. So typically with the Earth, this distance right here, from the focus throughout here, our perihelion, is 147 million kilometers. And the distance we are at aphelion, which is the farthest, is 153 million kilometers. So what we want to do is write an equation for this, and we're going to put the origin 0, 0 at the center of the solar system. Not at the Sun, that's at a focus, but at the center of the solar system. Okay, now if you remember, this whole distance here is 2A. So 2A equals the distance from my focus out here is perihelion, and the distance from there out to there is aphelion. So the distance on the major axis is basically perihelion plus aphelion, or A is going to be perihelion plus aphelion over 2. Okay, well this is kind of a nice thing to do. Let's go back in, and while we're at it, we want to write an equation. Let's go ahead and get A. So A is going to be, and we'll deal with millions of kilometers. It's going to be 147 plus 153 over 2. It's going to be 150 million kilometers. And that gives me A. Okay, now what we need to do is to find either B, well that's not going to be possible, or to find C, which is the distance from the center Okay. Now, what we do now, we have A, right, which is this distance from the center out to here. We know the distance from the sun out. So C is the distance from the center to here. So C is going to equal to A minus our perihelion distance. Or C will be equal to 150 minus 147, which will be 3. All right, we can get B from this. Okay, what we know is that C squared equals A squared minus B squared. I solved for this once. Last time around I moved my B over. It's going to be A squared minus C squared, and B squared is what we want. So we start plugging in. B squared will be equal to A squared, 150 squared minus 9. Or B squared will be equal to whatever that works out to be. Okay? And that's the number you put down below here. Okay. And once you get that number, which is 22,491, we need A squared, which is 22,500. So we're horizontal, so I'm going to have X squared over 22,500 plus Y squared over 22,491 equals 1. And I calculate my eccentricity, which is going to be 3 over 150. And you can calculate that. And as you can see, we're really not that far out of it. So this is the kind of thing we will be dealing with when we're dealing with that one. Problem 48 has always been a problem for people. Here's the key to working problem 48.